Thank you, Shinji Suzuki.
Now,
let's have the ceremony for the Daniel and Florence Guggenheim Lecture Award. First, Shinji Suzuki will talk about the lecture and award. We will play a video. After that, we will have a live connection with Shinji to host the ceremony. Now the video.
I would like to introduce the Daniel and Florence Guggenheim Memorial Lecture. As it's founded in 1957, ICAS established the Daniel and Florence Guggenheim Lecture as its distinguished lectureship award in recognition of the great support that ICAS received from the Daniel and Florence Guggenheim Memorial Fund for the promotion of international cooperation in the aeronautical sciences. This is a historic board of the Daniel Florence Guggenheim Foundation. The foundation was established in 1926, supported research of many areas of aeronautics. You can find Charles Lindbergh here and Orville Wright here, of course, one of the Wright brothers. This is a very interesting picture. The first Daniel and Florence Guggenheim Memorial Lecture was delivered at the first ICAS Congress in Madrid, Spain, by Professor Theodor von Karman, one of the founding fathers of ICAS. The subject of the lecture was some significant development in aeronautics since 1946. On this occasion, the Guggenheim Lecture is to be delivered by Xinguo Zhang, Chief Scientist of Chinese Aeronautical Establishment and Distinguished Professor. On this occasion, the Guggenheim Lecture is to be delivered by Dr. Xinguo Zhang, Chief Scientist of Chinese Aeronautical Establishment and Distinguished Professor of Tsinghua University, in recognition of outstanding contributions in leading the practice and promotion of model-based systems engineering and enterprise systems engineering with digital transformation in aviation industry of China. Dr. Zhang is the former EVP and CIO of Aviation Industry Corporation of China, AVIC, and former president of Chinese Aeronautical Establishment. He is also the vice president of CSAA, Chinese Society of Aeronautics and Astronautics, executive committee member of ICAS, president of INCOSE Beijing chapter, AIWA fellow, Royal Aeronautical Society fellow, INCOSE expert systems engineering professional, and TOG certified distinguished architect. Dr. Zhang has been working in aviation industry for 40 years. He is recognized as a leading complex systems engineering expert, both in China and overseas. He focuses on developing and applying methodologies of enterprise architecture, system of systems engineering, and model-based systems engineering to solve complex system engineering problems with very high level of creativity and have great achievements. As former EVP and CIO at AVIC, Dr. Zhang architects the digital engineering strategy and carry out the digital engineering transformation in Chinese aviation industry, which has been expanded to many industrial domains. Moreover, his efforts have profoundly influenced government policy in industrial innovation and transformation. Due to his tremendous contribution, Dr. Zhang He has given the Founder Award in 2018 at the 28th International Symposium, while his co-authored paper, Handling the COVID-19 Crisis towards the Agile Model-Based Systems Approach, has won Infosys Systems Engineering Journal Outstanding Paper Award in 2020. So, Dr. Zhang, please start memorial lecture.
Award. 接下来我们就有请张博士来接受 Daniel Guggenheim 这个奖项。
Since I'm not in Shanghai, I'm very sorry. I could not hand him the certificate. Mr. Lin Zoming, a president of CSAA, will hand over that instead. Dr. Lin and Dr. Zhang, please come on to the stage.
Thank you, Mr. Lin Zuoming, for presenting the award to Dr. Zhang on behalf of Professor Suzuki. This brings us to the end of the opening ceremony. Dear delegates and guests, we will now move on to the next session of the Congress. So, our staff, please get ready for the keynote speech session of the Congress, and we will allow our leaders and important guests to leave first. Thank you.
Good morning, ladies and gentlemen and friends. It is a great honor for me to have this opportunity to share with you for some digital engineering transformation and innovation in the past 10 years in aviation industry of China. I will tell you why and how we did it and how much achievement so far we have got. The system we are facing, especially in aviation and the defense industry. I would believe most of us once were very familiar with the system, but for past 10, 20 years, more and more we're dealing with system of systems. For example, the air traffic management. We used to dealing with physical system, whatever is system or system of system. But now we are feeling that the organization or enterprise we are working in, which actually is even more complex system because this involved not only technology, but the people and the process as well. So the total complex system should include all of them. And that is why I would cover the digital engineering transformation based on the international industry coordinative model, which should include the enterprise management X, value chain X, and product and lifecycle X. So to dealing with a digital transformation today, we cannot only dealing with, we call it a physical system alone. We have to dealing with the enterprise system, which is our organization itself. For both, we need a set of common core technology. I would like to raise the architecture, model, process, and the data as the four core common facts to describe this. First of all, let's take a look at what is, we call it engineering system. That is what we are dealing with our products and service. For digital design and manufacturing, we have been working on this for about 10 years for model-based system engineering and model-based engineering, even model-based manufacturing as well. In order to separate the digital and the physical system, then we are going to design, develop the digital twin for different level of abstraction to cover all the life cycle of the products and the system. Of course, we cannot only have the digital twin itself, we need a digital thread to connect all the models in different level and the different phase of the life cycle of the system. I think most of us are very familiar with the system engineering process. Originally, it comes from software engineering. We call it a V process. Maybe just by first looking or by imagining that we think this V process should be very smoothly or continuously. But as a matter of fact, it's very, very fragmented. We can call it all the activity actually do not really very close connected to each other. So sometimes, ironically, we actually working on, we call it system engineering, but the system engineering process itself seems not a real system because many people are working in different domains and in different disciplines. And the people come from different backgrounds. And for a long time, they cannot talk to each other, cannot understand each other. That is a big problem. And the root cause for this, of course, is many. One of the major issues is that for many, many years, system engineering actually start from requirements to specification to design all the way based on documentation. So what is the problem with the documentation? The lack the clear definition of the requirements, also lack of the common understanding because people are working with different disciplinary language. And because we do not have the clear system architecture on top-level design, so we do not have a system model to cross different domains. And in this case, it's difficult for us to find out what is wrong at the beginning, but we put most of effort in late phase of the system engineering life cycle. Based on all of this, it's very much difficult to build the traceability from the very beginning, the requirements to design, development, manufacturing, operation, and maintenance. So it's, again, even more difficult to face the change in management. Even up to today, a lot of projects still have the problem with change in management and configuration management. All of these issues actually is because the traditional paradigm for system engineering is based on documentation. Some people sometimes even make a joke that the engineer could finish their job, but cannot finish the documentation writing, right? So that's very sad. As we have documentation in our hands, we think that everybody read the same language and the same documentation. And because of a document was written in natural language. And the natural language, even we have same words, but every people in different discipline and with different background were interpreted in their own way. So that means many people in different branch, domain, and discipline could not really have the common understanding even within same documentation. That means we think we talk same thing, but actually we talk different thing. If we have model, as ICAS has a definition, should from very beginning, from conceptual modeling, it's not from the disciplinary modeling. That means we need graphic formal language to build a common model. And everybody will see same picture, speak same language, and have the common understanding at the very beginning on the top level design. Because this step will decide we do the right thing. And later on, we will try to do things right. This does not mean we do not need the documentation anymore. We should have a model first. Then we will generate documentation automatically. That is the way we are going to have the new approach of working on the model-based system engineering. And that is many institutes are working on today. So what has been changing for model-based system engineering? Because traditionally, during stakeholder requirement and system requirement, even to system architecture, we only have function analysis and a structure design of the system. We have to divide all the function to all the discipline and the domain to start different design and manufacturing until late phase of the life cycle. During the integration, we can show the behavior. We can verify the dynamic of the system. That's the old way. The new way is we move the system behavior and function to the very beginning, which we could not do in the past because we do not have the language to describe, we do not have the tools to support. In this way, we don't need to iterate from a left side of a digital domain to right side of physical domain, because this iteration takes months, years, and spend huge of money and huge of time. And that is why the aviation industry, for the project, a typical project, we still need 10 years to go. In the future, we may need 4 or 5 years to finish one of the project. And that is very possible, because we take more iteration on the left side of the digital domain, and in this way, we actually increase the maturity of the technology and reduce the risk. Based on model-based system engineering, we need to follow rigorously the logic from requirement, stand R, function, stand F, logic, stand for L, and P, stand for physics. So from requirement to function, to logic, and to physics, or to products, that is the logic we need to follow. And that is a way to dealing with, we so-call it forward engineering. Because in the past, the engineer are urgently or eagerly to approach the physical level, eagerly to approach how to do it, to take what kind of advantage of technology. But today, we need rigorously start from requirement to make analysis of what is the real needs from different stakeholders and what function the system should have to support the needs of the stakeholders. This too actually is a problem domain. And if we make working on the problem domain or problem space, we should not consider what kind of technology we're going to use. This has to be done later on. So from the logic to physics, then we need to divide the function to the logic. And even at this level, we don't need the concrete technology to make implementation. And to the final level, the physical level, this is so-called the product level. So that is a new way we need to work on, based on the model-based system engineering. And I believe that many institutes in the past 10 years has been working on this procedure. I could see the audience today from COMAC, Commercial Engine Company, and the Shanghai Avionics Institute. All of you actually already work on this. Now we have to solve one of the critical problems. At the very beginning, I said we do not have a common language. That means we do not have a common language for the people in different domain and discipline. But now we need to build another common language which could between the human, the project in real words, and a symbolic system within computer. So that means what in our mind, what's going to be put in computer for modeling and simulation, what exists in the real world. This three has to be the same meaning. So the question is how to do it. So we need a formal graphic modeling language. The new transformation, digital transformation, is different with the old version. Now we have international standard to have the standard language, modeling language, which is independent of software vendor. We do not need to rely on the concrete vendor. As long as you learn and master this international standard language, actually you can describe the real system with what we're thinking and with what put into computer to modeling and simulate. This actually related with our cognitive integrity. Whenever we try to recognize something, the minimum ontology actually need only two things. One is form, another one is function. The form means what it is. The function means what it does. As long as we have these two, we understand and recognize the characteristic, the feature, the property, and so on. So these two actually mean the cognitive integrity. But again, we have to put them together instead of separate them. I will explain this later on. So now, another question is, what is a sequence or logic that we start working on? The form should always follow the function. That means we have to start from the function, not the form, or not the structure. But most of the time, a lot of engineers still do it in the opposite way. Start from the structure, and then go to function. So this is, they call it architective logic. And this logic has been for 100 years in the architecture or building industry. So in this way, we need a very systematic thinking. And the sequence and the logic should be like this. If we face a system, let's say one of the aircraft, or a system of system, whatever, we should start, we call it a black box. And we should first see what is the context. How many systems is going to work with the system we are working on? And this time, we are focusing for what the purpose of the system. After this, we should go to what it does. This is the behavior-focused description. We mainly focus on dynamics and process. So the first thing, which means what is the purpose of the system. Second, we were dealing with what the system does or support the purpose of the system. So this is very logical. And finally, where it goes to, we call it structure, whatever, or how system consists of, or how it is built. Again, unfortunately, in the past, many times, a lot of engineers actually start from the last one instead of the first one and the second one. So do not follow the real logic. So today, how do we work on this? The international standard from both ICAS and OMG developed the system modeling language. Actually, this is, from the name we can say it's a system modeling language. This is the first time in human history that we have the language to describe a system in the conceptual level. We can see that this language exactly starts from a function view by use case. So the function from the user, from operator, not from the designer and developer. That is very important. And then if we have the function, because the function is abstract, how to describe the function? By behavior. As long as we describe the behavior with activity, sequence, and state, then we will map all the behavior to structure. Of course, later on, we will check how this structure, or within the structure, the interaction and the relationship between the elements of the system structure will support the behavior and come back to support the function and again to support the system purpose. So this is the purpose of system model. In aviation industry or in aircraft design, we have a lot of disciplinary, aerodynamic, structure analysis, and system design. How this different perspective and different point of view will work together to make alignment to the system model on the top level. That is a very challenging issue from the very beginning, and that is what we're doing in the past 10 years and now. As long as we have system model, then the system model could map to software model and hardware model. Many people, once we discussed that we have model for many years, what is new? But the original model are all of them within different disciplines. They cannot talk to each other. They cannot integrate. Even the data are fragmented. So within the system model on the top level, all the model will have the root. That is why they call system model the single source of truth in system, and it will work in a total life cycle of the system. So based on models and rules across the system life cycle, from very beginning to the end, or cover the all phases. In this case, we can build the complete traceability. And this we cannot do it in the past based on traditional documentation-centric engineering method. If we can do this, or we have done this, that means we can dealing with evolution of complex system engineering. Because in the future, especially for the aircraft design development, it takes many years for the design development, manufacturing, and again, they take many, many years for operation. So one way, the requirement cannot be fixed, and the requirement will change. For example, this time when we face the pandemic, COVID-19, people suddenly find that in a passenger airplane, if someone affected by COVID-19, and even no place to isolate, right? And the people in the aircraft, all of them will be infected. So what do we need? So again, that is a new requirement. So there are many, many reasons that we need to change the requirement based on the new function needed, the new performance, reliability, usability needed, and change it. Another issue is technology. Every product has the life cycle of, every technology has a life cycle too. And the software, electronics, material have different life cycle. If we keep the same life cycle for the aircraft, which means we cannot accommodate new technology, right? So we need to have open architecture to introduce the new technology anytime, anywhere as needed. In this case, we have the new way, call it evolutionary development procedure. So based on model-based system engineering, we actually support the paradigm shift of Industry 4.0. In the past, or even the near present, we did the less job on the left side of a V, and we spend most of the time on the right side of the V in the physical domain. Even today, we call it, we have digital mock-up of aircraft, which actually is digital geometry prototype. And again, we follow the traditional industry pattern, which means design first, build second, then test and verify. In the future, we need to do more work on the left side of the V in digital domain, and we have much more iteration to increase maturity and reduce risk of the technology. And in this way, we do not only have digital geometry mockup, the digital mockup should include geometry, function, performance as well. That is what we call it a digital twin in Industry 4.0. And in this pattern, we're going to change the traditional industry approach from design first, but not build directly. We make virtual test or virtual integration, and afterwards, we will build the physical products. In this way, we do not need the many times physical prototype, maybe just once. We can imagine if we just reduce one cycle of the physical prototype, we will reduce at least 2 to 3 years the development time and a lot of money as well. Of course, we reduce a lot of effort as well. So the digital transformation application from concept to design to execution. Pre-validation and a multi-party trade-off analysis based on virtual validation and engineer validation, even during conceptual phase. During the design stage, we actually could do cross-discipline design and rapid integration through model-based research development solution. During the building and execution, we can connect equipments, collect data, and achieve real-time control and solution. During operation and service, we can study and flight data, virtual training, maintenance simulation to improve service data and management. All of this, we should do it in digital domain first, then goes to physical domain. So the MBSE applied in aviation industry of China for about 10 years. More and more major aircraft programs now working on model-based system engineering, and it has got a great achievement so far. Include a lot of audience today. So let's move to the second part. As long as we're dealing with our products, which is aircraft design and development, then we have to think about our organization itself, which is enterprise system. An enterprise in complex system engineering does not mean it's a company or it's a firm. It should be all the complex organization for human being. We need to reshape architects so the same system engineering process will be used, but within different tools and methodology. Again, we have to analyze what is the complexity for the enterprise system today. Even our organization now, for all this organization department or system engineering department or project management department, and we have many years different management innovation tool. Every 2 to 3 years, we launch an initiative. Everybody call it a management innovation. But so far, for the past 10 years, we have many new methods, new tools. But what is the relationship? What is the relationship between management tools and the strategy? What is the management relationship between management and the system engineering? Even For the past 30 years, we work in digital domain. We can think so far, or some years ago, we still face a lot of problems. A lot of digital tools actually is pieces, fragmented. People work in different domain, working on their own subject, use their own digital tools. For the total organization, for the total enterprise, you cannot integrate all the tools. They cannot work together. Again, you cannot integrate the model and the data. So recent years, I heard a lot of people, instead of talking about intelligent manufacturing, they talk about intelligent institution, right? So what is intelligent enterprise? There has to be integrated enterprise. If we cannot integrate the enterprise, you will not be smart. Again, you will never be intelligent. So the enterprise architecture will help us to approach the digital transformation for our organization. On the left, we have silos, pieces for all these tools and innovation method. By taking advantage of enterprise architecture, we can integrate them to business capability, component-based architecture description for strategy level, business level, information level, application level, and the network level. And this will help us to dealing with what is our IT system, with our engineering and management system, and all the way to align with our strategy. So the new model for enterprise system, exactly the same principle as what we did for our product system. We need the top-level model, which is architecture modeling for our organization from strategy, vision, and mission. Then all the way, we need to build all the process modeling to implement the strategy. For many years, even we implement the ISO, quality insurance, 9001 series insurance certification. But the process improvement never get touched with the IT system for many years. So finally, as long as we have an architecture model, all the business process model, then we could go to the IT system or software modeling to implement. So we will have task domain, method domain, and a standard domain based on all the international standards. We have been working closely with TOGAF, the international standard for enterprise architecture. Within the architecture content Metamodel, we can see clearly from top level is architecture principle, vision, and the requirements. This, again, is like what we're dealing with aircraft design. What is different? We can design a new aircraft from scratch, but our organization is always there. We cannot start from zero. Then the architecture requirements goes to the next level, first dealing with business architecture, which includes motivation, of course, as drivers, goals, objectives, and measures, and organization. So the third level is behavior. We can try to think most of our organization. They have the organization chart, but they do not have the process architecture. They cannot describe their behavior. After we have business architecture, then we should implement in information system architecture. Even up to today, quite a lot of organizations do not really implement the IT system, follow the enterprise architecture and the business architecture. Then finally, we should implement technology architecture, which we're dealing with hardware infrastructure. And this again should, from the conceptual level to logical level to physical level. So you can see again a lot of similarity between the system engineering for our products and the system engineering for our organization. But in the past, we never do it in the same way. So the TOGAF architecture development methodology and the language called ArchiMate. We're mapping these two together. And the ArchiMate language is a language to describe our organization. And again, we can see the two key points, behavior and structure. It's the same meaning as I just explained, is a form and a function. So we can see whenever you try to describe the physical object, or you try to describe the object or conceptual object, you always need at least form and function, or structure and behavior. So the ArchiMate framework will take the cross-domain mapping between the language, semantic, and the syntactic to the architecture development methodology. In this way, we can develop our own enterprise modeling framework. On the top level, we need system evaluation for enterprise competence, improvement, and success. We need a structure which comes from our strategy, vision. And in the second level, we need to describe our system behavior. This is the behavior of our organization, not physical system. So we have function relationship, logic relationship. And the third level should be system structure. But usually, we from strategy goes to structure directly without system behavior description. Again, it's a similar issue as what we had for the aircraft development in the past. So this is what we have done in aviation industry of China 7 years ago, based on TOGAF architecture to describe the core architecture model from strategic architecture, business architecture, application, technical, physical, to data, to standard, security, and governance. And this implementation of enterprise architecture has got a highly recommendation and recognition from the TOGAF. So the digital transformation of enterprise system at the very beginning, I said, with all the axes include enterprise and the value chain and the product lifecycle management. So we need the business integration in the middle. We have business intelligence on the top, and we have connection at the bottom with IT system. So how to implement all of this? One example is to manufacture. So on the left is what we take the moving production transformation from originally stationary aircraft manufacturing process to the moving production process. That's supported strongly by information system. On the right side is what we call it flexible production system, which based on cyber physical system, again, based on information system, to make the flexible configuration for the production. Now we can think in the past, we take IT technology to dealing with our products. Now we take IT or new technology to dealing with production system. How to do it? So the product, the digital twin, will grow up with progress. Now, it's very popular in Industry 4.0 about digital twin. But where does the digital twin come from? The digital twin DNA actually from requirement, right? And digital twin was born during the design, and it grew up during manufacturing. Actually, the digital twin will be used during the service. So that is the whole life cycle of a digital twin we have to work with. The digital, as I said, we are not only dealing with the products, production. Again, we need a digital twin for our process and even for our enterprise. Same principle, same methodology, but different object. If we have the total modeling of our business process, and we have the process plus all the enterprise architecture, then we're going to build the digital twin of the process and the enterprise. So the enterprise modeling system and business process will support the transformation and innovation for whatever the industry transformation, management innovation, and industry 4.0. So in the past 8 years, we have supported the AOS pilot program with BPM and architecture, come from process ontology, which actually be shared with all the substitute company within aviation industry of China. The AOS full life cycle have 37 steps in 6 stages and have all the modeling tools. Now, the 20 pilot program has got a great achievements, and that is why another 40 companies are following now. And this even encourage a lot of industry outside of aviation industry to follow. So the model-based enterprise framework, after many years of research, development, and implementation, we have enterprise architecture-based methodology from strategy, business, application, data, technology, and management on the left. We will have enterprise modeling system-based organization model from mission to capability, requirement, business, process, and IT. I believe that most of us are very familiar with the left side of the factors, but we do not really completely familiar with the right side of the factors. And we have to make sure that these two sides very much close and coherent to each other, and supported by shared method, model, opportunity, on the bottom line from the business support. On the top, all of this, whatever the reference model, model BPMN, UML, method TOGAF, model ArchiMate, reference model, and method BPM, data management, all of them are correspond or follow the international standard. This is very important because the international standard has collected all the experience which has been mature in the industry for many, many years. So if we combine these two together, we can see that on the left is the engineering system, on the right is the enterprise system. And finally, we need to integrate these two systems together, even based on same principle, same methodology. But they may use or take advantage of different tools On the left, we use Sysmel, Modelica for multiphysics, UML for software, AEDL for embedded system, and VHDL for electronics design. On the right side, we will use ArchiMate for architecture modeling, EPC for architecture, BPMN, and UML for business process, presentation, and modeling. In this way, you can compare the two sides. For the system, we start from an operation concept model, but for enterprise, we come from vision model. For system, we have system model, but for enterprise, we have organization model. So all of the facts are corresponding to each other, but describe the different object. So all these models make sound system and agile process. So to finalize, the digital transformation methodology from the past to what we are doing now and go to the future. The digital engineering transformation mainly dealing with model-based system engineering for our product system and model-based enterprise system engineering for our organization itself, supported by architecture, model, process, and data. So if we look forward for the future, we hope that in the physical world, we have wisdom of flying. In the digital world, we will have the flying of the wisdom. So that's all for my report. Thank you for your attention. Thank you. I will be more than happy to take all the questions, please. Professor Suzuki, I cannot hear you.
Impressive lecture. Digital transformation, DX, is challenged not only in aviation and aircraft industries, but also in every industrial domain in every aspect. So I will accept some questions from the floor or from the internet. If you participate on the internet, please write the question using the chat function. So please identify your name and affiliation before questions.
Please, the lady in the second behind Mr. Chen Yong. Anybody have a microphone? Here.
Hello. This is Grace Zhang. I'm the COO of Long-Rise Avionics Company. Thank you so much for talking about MBSE. I have a question related to the airworthiness certification. Probably you know about because the increased complexity of the design and the modern aircraft, and this is why there is became more and more important to you MBSE. But at the same time, the traceability is very important for the airworthiness of aircraft, and this will be the balance of the convenience of MBSE versus the traceability of the software design, architecture design, aircraft design. How is the Chinese aerospace community is increasing to solve this problem?
Thank you. Thank you for your question. Actually, the model-based system engineering initiate from the industry for, at least in the West, about more than 15 years. Inside of China, about 8 to 10 years up to now. But the issue is how to implement MBSE with original, not only the design development procedure, but also how to comply with airworthiness certification, right? That is going to be an international issue. But we can see in the past few years that the international airworthiness agency, for example, the FAA in US, EASA in Europe, already launched or raised a future direction, which means in the future, the certification for aircraft is not only based on test. They call it model and simulation-based certification. That's a new name. Of course, come from new meaning. The reason is, in the past, we certify aircraft based on, all of them based on test, to verify the design, the manufacturing, to make sure that everything is okay. But as I explained at the very beginning, from the requirement to system specification, we did not have model. And we did not do it as we did for mechanics, for electronics, for software, to model, simulate, before implement. What does this mean? That means the requirement itself is not verified at the very beginning. It's like a kind of assumption. Suppose this is okay. Then we do the real job. And finally, we hope through the test to prove that the requirement design is okay. That is too late. If we start from beginning to describe by use case, we call it use case, which means where is the system boundary? Who is going to use this system? What is the interface between the operator, user, and the system? What is the context? In this way, we understand fully how the system is going to work. Based on model-based system engineering, we have to start from a use case. We have to describe it, we call it scenario. In Chinese, we call it 用力和场景. So today, they call it use case and scenario based or driven requirement development. So in the past, we call it technology development, right? But today, we would say we need requirement development. We need to develop what is the requirement. Because the requirement will actually decide what is right for the customer. And later on, what we did is how to do it in the right way. Even you do things in the right way, but you do not do the right thing. What does it mean? That means you do things in the right way, but it's not a right thing. So you should first make sure that the requirement is okay. Understanding of the requirement is okay. And everybody have the common understanding, and then later on, there's no mistake. Right? So, in the future, not only I believe, actually, all the civil aircraft, or even the military aircraft, if you want to go to certification process, you cannot only just to show your test result. you have to show how the requirement started. What is conceptual modeling at the very beginning, and how the conceptual modeling or system model translate to different and every stage, even to the operation and the service. So that is why now all the airworthiness agencies work very closely with industry. How to take advantage of model-based system engineering to improve the certification of the aircraft. So I hope I answer your question.
Okay, thank you, Dr. Zhang. I have a question from the internet. So he or she says the changing requirement is very important. Some of those requirements can only be identified through cross collaboration with users, aircraft operators, and manufacturers. And how do you proceed facilitating these cross connections between research, academia, and industry? That is the question.
Okay. So that is why we need a system architecture. The international standard, both from ISO, IEEE, OMG, INCOSE, all of this international standard organization actually share the same definition for architecture. The architecture means every system has a mission, has the context or environment to work, and every system actually has many stakeholders. The stakeholder means the user, the operator, people who maintain, and the designer, manufacturer, all of these roles that people play in the system. But the question is that the different stakeholder will have the different concern about the system, right? Because the different responsibility will decide the people to pay attention to which area. So how to describe the different concern of the different stakeholder? We will call it viewpoints. That is the terminology for the architecture. The viewpoint means from where to see. Then we have view. What is a view? It's what we see from where we see. You can see the scenario. And if we have the scenario or view, different view, then we can build a different model to describe the different views. And all the way collect different concerns from stakeholders, different viewpoints, different views. We will call it architecture description. The architecture description, because they collect all the views, all the concerns from all the stakeholders. What happened? If we put everything on the same page, we will find out what is a conflict, what is a problem, what has been missing, where is the overlap. Somewhere maybe very much redundant overlap. Somewhere we're still missing, and a lot of area have a contradiction or conflict. Now, we should collect all these stakeholders together to solve all of this problem until we get completely agreement. No conflict, no contradiction, nothing missing, nothing more, nothing less. Then we have, that is called it architecture description. After this, we will have, we call it system architecture. This will become a top-level system design in the conceptual level. And again, we do not need maybe only one architecture. We need more than one architecture to make trade-off, to make selection. Because for the complex system, we could not guarantee that we have most advanced technology, we have most short time to develop, we have the lowest cost to spend. We cannot do that. You have to choose. You have to make sure what is your priority. Is the technical advantage should go first, or the time frame should go first, or the cost should go first. So again, we need a kind of trade-off or compromise to make sure that what really the customer or the user care about. That we call it the customer satisfaction. So that is why we need the architecture at the very beginning and on the top level. And the architecture actually become a bridge to help all these people later on operate, use, maintain the system, and all the people who design, manufacture the system. Everybody could talk to each other, see the same picture, speak the same language, have the same understanding about the total picture of the system. Okay?
Okay, Dr. Zhang. Can you find another questions from the floor? No question from the floor? Okay, I have one question from the internet. So what is the competency requirements for the aviation professionals during the digital engineering transformation? Yeah, that's a good question.
Can you repeat again, Professor Suzuki?
Sorry. What is the competency requirements for the aviation professionals during the digital engineering transformation? Competency. Yeah.
Okay. Speaking about competence, I think that we have in the aviation industry, we have a lot of system engineers. But as I said, in the traditional system engineering, we pay more attention to process itself. Everybody knows what is the first, what is the second. We follow all the development procedure. And we know what is the method and tools to use. But for model-based system engineering, we need changing our mindset. Instead, to do the real work late phase, we should start the modeling, structured description at the very beginning. And we need to train the system engineer with the capability of object thinking, abstract thinking. Because at the very beginning, all the model are actually based on the logic reasoning instead of to solve the mathematical equation. And in this way, as I explained at the beginning, in order to solve the complex problem, we need a different level of abstraction. So the requirement level, function level, logic level, physical level. And at different level, we need a different way to describe. On the top level, we may need only this form and function. But later on, we need to allocate function to logic. That means we need to divide the function to the logical level. Sometimes we call it modularization or partitioning. But this is different as what we did in the past. Because this were based on module, we have to have the principle, we call it how to describe it in a mutually exclusive and collectively exhaustive, sometimes called the MBSE methodology. So from the top level, conceptual level to logical level, this two level actually was somehow missing in the past. And again, as I explained for the first question, we need to train ourselves, especially for people who are working on the top level, to familiarize with architecture, knowledge, tools, language, and training as well. And that is why in the past 10 years, we have been trained thousands of system engineering and aviation industry of China. And I believe so far, more than 500 system engineers has passed the system engineer certification from International Council of System Engineering. So I hope that more and more system engineers should train themselves both in the methodology, the language, system language, try to describe the system in abstract way in a conceptual level, and to work closely with subject expert or disciplinary engineers in the late phase. Is that okay?
Okay. Thank you, Dr. Zhang. So